What the aspect ratios of?
Yeah.
Oops.
Lightcone state was closer to infinity.
That's slightly better.
Slightly only slightly.
Okay.
Come on, consider he's German. He cannot say that something that is possible.
Okay. Thank you very much for the opportunity to present this. There's two main topics I want to talk about. One is G versus Jaffe-Manohar. Some of you have, or many of you have perhaps heard some of these results. I'll try to be brief, but then I want to spend most of the time talking about twist 3 because we found some really weird results in that context, especially some singularities in PDFs and GPDs in twist 3. Hold on. I hope not. I think it will be fine. Something is wrong, but it's okay. We've talked a lot about spin decomposition, so I'll jump right into it. The reason we have more than one spin decompositions is illustrated here. What's on the left here is in QED, what G would call the total angular momentum carried by the photons in QED. And that's just the Poynting vector cross product with the position integrated. And you can express the magnetic field in terms of the vector potential. And in the next step, I evaluated the double cross product in the square bracket. I didn't touch the R cross yet, so it's still there in both terms. And if I use the back minus cab rule, I get these two terms here, and I was careful that the derivative only acts on this one, not on that one. That's why I wrote the first term in this weird way. This one here, I left as it is because it already has a very simple physical interpretation. This is the gauge field, that's the conjugate momentum for the gauge field, and the indices are contracted, and in between we have the orbital angular momentum operator. So this term has direct interpretation as the photon orbital angular momentum. The second term that I get here, to simplify it, I do an integration by parts, which gives me two terms, one where the derivative acts on the electric field, yielding the divergence, and one where the derivative hits the position operator, and after some algebra, you wind up with the cross product between the electric field and the vector potential, and the position operator is gone. And so this one I talked already about, it's the quark. It's the electron orbital angular, it's the photon orbital angular momentum. The last term here only acts on the internal indices. It mixes the internal indices up. So this one actually has the interpretation as the photon spin. And then we get this term here, which using the equations of motion, divergence of electric field is the electron charge density. I can write in this form. And if I write it in this form, it cancels a term that's already there in G's decomposition, namely in the quark orbital angular momentum, and it makes this one here disappear. And so what I've done is I've not only decomposed the photon's angular momentum into an orbital and a spin part, but I've also generated a term which cancels part of the quark orbital angular momentum. So in some sense, I've shuffled angular momentum from the photons to the quarks. And that's the essence behind the difference between the G decomposition and the Jaffe-Manohar decomposition. G, the orbital angular momentum in the G decomposition contains the vector potential. Jaffe-Manohar doesn't. It doesn't look H invariant, however, one can write down a gauge invariant extension for each of the terms in the Jaffe-Manohar decomposition. Now, looking at the fact that we have two different decompositions, questions arise such as how significant is the difference between these two decompositions? And the progress in this direction came based on Wigner distributions, because Wigner distributions allowed to discuss both angular momenta, orbital angular momenta in the same framework, and that allowed us to directly see the difference between them. And, oops, what is this? So, Wigner distributions are defined like pattern correlation functions, except you're looking at non-forward matrix elements. And the non-forwardness via a Fourier transform gives you information about the position of the quarks. And once you have Wigner distributions, you can calculate TMDs by throwing away the information about position. You can get GPDs by throwing away information about the momentum, and the orbital angular momentum just by evaluating the expectation value of the cross product between position and momentum. And because it involves a non-local correlation function, we need to insert a Wilson line to make it gauge invariant. The most simple way to do it would be a straight line connecting these 2 points. It turns out if you do that, you get the G orbital angular momentum. However, many motivations why one might consider a staple that goes to Lightcone infinity and back. One being that this gives you TMDs that include the final state interactions. If you do that for the orbital angular momentum, you get, it turns out you get Jaffe-Manohar. Intuitively, you can see that because in Lightcone gauge, these links that extend to infinity and back don't contribute in Lightcone gauge, which is the gauge in which the Jaffe-Manohar decomposition is usually formulated. Of course, there's the link at Lightcone infinity, and in fact, Jaffe-Manohar, Jaffe himself, with Bashinsky at some point worried about that, because the Jaffe-Manohar, when you select the Lightcone gauge, that's A plus is equal to 0, you have not completely fixed the gauge. There are still residual gauge transformations that leave A plus equal to 0, but change the gauge transformations where you add to the derivative of a field that only depends on the transverse position. And so because of that, just selecting Lightcone gauge, you haven't completely fixed the gauge. And to address that, Jaffe and Bashinsky wrote down a definition of quark orbital angular momentum that involves the zero mode of the transverse gauge field, which is defined like here, the average of the transverse gauge field along the Lightcone. And that turns out is equivalent to the taking the average in minus infinity plus infinity of the transverse gauge field, because in this integral is dominated by its asymptotic values at plus or minus infinity. And since it doesn't matter in the definition of orbital angular momentum whether you include this one or that one, you might as well take the average. And that's why the Jaffe-Manohar-Bashinsky definition of orbital angular momentum is equivalent to including a light front staple into the Wigner functions. If you now look at the difference between the two, that can be written as a matrix element that looks like a true Sturman matrix element that appears in single spinor symmetries, except that there is a cross product with the position here. And the particular linear combination that enters here, the particular linear combination of electric and magnetic fields that enters here is nothing but the Lorentz force for a particle that moves with the velocity of light in the minus z direction in the transverse component of that force. So what this difference here represents is the torque that acts on the active quark in a DIS experiment as it escapes to light front infinity. And it's integrate along the trajectory of the quark, and for relativistic particle, time is position. So that integral is equal to the change in orbital angular momentum due to that torque. And now I think I might need some help from, on which one? On this one? Okay. A student of mine made this movie to illustrate that this torque is non-zero. So I played several times because it's a little bit fast. So what you're looking at is an electron that's polarized in this direction, and we're looking at the magnetic field of the due to the magnetic moment of the electron. So these lines here are the magnetic field lines, and what these are, they represent an ensemble of positrons that are being struck and moves through the magnetic field of the electron. So restart it, double click. Click. Yeah. Okay. So the positron that starts out here feels a magnetic field that goes this way. And so if you look at the Lorentz force, V cross B, the force points this way. For this one right here, V cross B, the force goes that way. And if you look at positrons that are struck and move through this magnetic field, you get this pattern for the direction of the Lorentz force due to the magnetic field here. And what you can see is that the net force due to the magnetic field, if you do the ensemble average, is 0, but there is a net torque. Okay, I think that was enough. And now we need to make this big again. And for a quark moving through the color magnetic field due to the spectators, one expects a similar result. You expect on average, some dipole field that's correlated with the nucleon spin, and that should result in a net torque. A couple of years ago, we did a calculation for an electron, and the result that we presented was that for an electron, you get a difference between these two orbital angular momenta. Actually, that calculation was incomplete. We forgot a term. G and collaborators did the complete calculation. The part that we missed is we did a Pauli-Villars regularization, which included a heavy photon. And a heavy photon has 3 spin states, not just 2. And we didn't include the light front wave function for the 3rd spin state of the photon. They did, and they did the calculation correctly, and they found 0 for the difference between G and Jaffe-Manoha orbital angular momentum. The immediate question, once I agreed with them, the immediate question that came up was, is this more general? And so what we looked at is, we looked at the scalar spectator model to investigate that difference. And we picked that model for 2 reasons. It's Lorentz invariant. It's comparatively easy. I mean, it's still a 2-loop calculation, so no 2-loop calculation is easy, but relatively speaking, it's easy. And also, that was the exact same model where it was first demonstrated that there's a Sivers effect in this seminal paper by Brodsky and collaborators. And Cedric and myself, we calculated directly the matrix element of the term involving the vector potential, which is the difference between G and Jaffe-Manoha. And we found some result, and I mean, the details are not relevant. The main point is that this matrix element, which represents the difference, is of the same order as the average transverse momentum. So this effect that the 2 orbital angular momenta are different from each other is as important as the Sivers effect. My colleague and his collaborators and former collaborators looked at the Jaffe-Manoha orbital angular momentum in lattice QCD, and the challenge that they faced was, as I explained earlier, we need a staple to light front infinity, and on a lattice there is no light front. So the way they deal it is, the idea is kind of similar to how people approach quasi PDFs or pseudo PDFs, but what you say is, okay, all I can do is calculate a space-like staple, but a space-like staple in a fast-moving nucleon is equivalent to a near-light-like staple in a nucleon at rest. And so what they did already a couple of years ago, they used that observation to calculate some observables related to the Sivers function and the Bohr-Mulders function. And these are examples for results that they obtained. So what's plotted here is the average transverse momentum obtained in a moving nucleon, and the x-axis is the length of the staple. And one can clearly see there are some asymptotic values that are reached. What you can also see is if the staple points in the opposite direction of the motion, the sign of the effect is reversed, which reflects the fact that the Sivers effect in Drell-Yan should be equal and opposite to the Sivers effect in Sidis. And evaluating something similar to that, just by looking at matrix elements that involve a momentum transfer, they get information about the position here, and by looking at the slope, they were able to extract both the G, that's at state length equal to 0, and the Jaffe-Manoha orbital angular momentum when you go to infinity. Obviously, this is not the final word. I mean, there's a lot of extrapolations that still need to be done. Small pion mass, make the nucleons faster. Those are just the most obvious things that's still need to be done. But what this calculation clearly shows is that non-perturbatively there's a difference between G and Jaffe-Manoha orbital angular momentum. Yes?
Sorry, kind of a stupid question. Why is the G orbital angular momentum correspond? Why does it correspond to the zero staple? I thought it's a straight line, right? If you just make the length of your staple to zero, you still have a corner angle. See what I mean?
Well,
I just misunderstood what you just said.
No, you correctly understood what I said. If you in your orbital angular momentum, I mean the orbital angular momentum is x integrated, so you don't have
Also, the two places,
the longitudinal position is the same.
I see. Okay.
So it's just an A transverse that appears here, and if you do an expansion of your exponential representing your derivative by finite differences, you just get the A transverse, which is exactly what's in the G orbital angular momentum. And if you do the same thing with Jaffe-Manoha, you get the gauge link at infinity, which is what Jaffe-Manoha-Bashinsky corresponds to. With the zero model. Okay. Now, I would like to switch topics and talk about twist 3. And there's several motivations to look at that. One is Polyakov and Pili some years ago suggested a sum rule alternative to the G-sum rule for orbital angular momentum, and it involves a twist 3 generalized particle distribution. I'll show a definition in a little bit. Another motivation to look at that is if you take the two-dimensional Fourier transform of twist 3 GPDs and you look at the x-squared moment, what you find is that you get some position space information about the transverse force. And I'm not allowed to talk about that because I was told I can't give the same talk twice, and I talked about it last week. So even though almost nobody of you was here last week, I will not talk about that. Sorry about that.
We can ask questions.
Yes,
you can.
And you can all watch the video on YouTube. I'll talk to the post it on YouTube. Your course.
Unfortunately, next week they're just.
After lunch, you can put the talk of Matthias here so that we can all.
I'll say a few words that hopefully make it more clear.
All right.
But this is just the main motivation, because everybody will immediately tell me it's hard. It's hard experimentally, it's hard in lattice QCD, so why should we care? And that's the reason.
So in this paper by Polyakov and developing the quantum model, do they show that this is a G's orbital angular momentum, not Jaffe-Manoha?
I'm not sure whether they make a point out of this.
Because I know one of the they work with quantum model, so there is no way of scaling which from they get this way. And my understanding of my paper with Yoshida is the one that showed this in QCD, and in that case, this is a G slope.
I would agree with that. I mean, we didn't show it ourselves. We looked at your paper and Polyakov's, and my interpretation of Polyakov was that it is G, even though I don't recall him stating it explicitly. It's simply because he only works with local objects, so there's no way a Lightcone staple can enter in Polyakov's approach.
Can I add a comment? We can see that as a pioneering work that was done long ago, and even the notation, you know, he didn't have a full parameterization of the twist 3 GPDs. So even that notation G2 is no longer.
You're just reminding you that you and my the two of you and my colleague Michael have looked at this more general for arbitrary staples.
Yeah, so that was done so long ago that of course he used he had a platonic picture in mind, and he had the that notation. So it's the very first attempt. I will put it that way. But then there was yes, what's his name? Yoshida's. You know Yoshida. Paper.
Sorry, but so for the rest of us, what's the answer?
G. This is G.
This is
Because you checked.
no, hold on. Yeah. Yes, we're both gonna talk about it, but that's G2. You cannot be very specific. That's what I'm saying, because that G2 is not even just the GPD that is used. It's like, you know, it's something. Okay. Well, that is something. That is, yeah.
The GPD G2 is defined using local operators. So there's no way you can get anything non-local, and it's defined gauge invariantly. So you must end up with something that's local and gauge invariant. And if you're asking about orbital angular momentum and you say local and gauge invariant, the answer is G. That's the short proof, but people have done a better job than the short proof. So this is how the G2 is defined. And I know this is ugly, but I just want to convince you that it is defined in some way. You look at some correlators and there are all these functions appearing. And so here's the famous capital G2. It has nothing to do with the lowercase g2, just in case you're starting to get confused. It satisfies some so-called Lorentz invariance relations, and they will become important later because what we find is that these functions contain delta functions at x is equal to 0. This is the relation I already wrote down, and we showed that the same relation should also hold in scalar Yukawa. That's important because that's one of the models that we use to test these relations. And what's also been suggested is that there's a relation between the orbital angular momentum distribution and G2. And I don't want to get into too many details because I would prefer to show you other details. But the short answer is, in a scalar diquark model, this is actually true. In the quark target model or QCD to one loop, this is not true.
So sorry, if the G2 contains a delta function, it doesn't contribute to the sheet.
That is correct. However, it's relevant in this context because if somebody wants to find out G2 from whatever little information they get, one of the points we're making, it's dangerous to impose this Lorentz invariant relation on G2 because that one does get affected by a delta function contribution.
Also, excuse me, why do you call them, those are the extensions, the generalized, I would call them generalized Burkardt copies of suppose,
Yes.
instead of Lorentz invariant relations. So the Lorentz invariant relations are more general, they depend on X. You know, they're not the independent.
I would be fine with
Okay.
that terminology.
Okay.
Yes.
Okay, yes.
I mean, it's, yeah, I don't like to say so many times Burkardt Cunningham because it's the wrong word. But it sounds like I'm bragging. So I would call what you call the Burkardt Cunningham sum also a Lorentz invariance relation, but it's semantics. Both is correct. Okay. A little bit about the force here, just because I can't resist. The the little g2, which is appears in the longitudinal transverse double spin asymmetry. If you look at the twist 3 part of G2 and you take the x squared moment of that, that gives you this matrix element here. And what's in here is, again, the same operator that appears in the Chu-Sturman matrix element, except evaluated locally. So it's the first integration point of the Chu-Sturman integral, which gives you, semi-classically, some information about the average force. And as I mentioned before, one of the motivations for me to look at twist 3 GPDs is if you look at the x squared moment of them and you take the 2D Fourier transform, you get information about how this matrix element is distributed in a transverse plane. So ideally, if one day we know how these twist 3 GPDs look like, we can draw force fields that show how the transverse force in the proton acting on a quark at a certain transverse position looks like, which direction it points, how strong it is. So that was the motivation we did all of these calculations. And I know spectator models suck. The reason we use the spectator model is because it's Lorentz invariant. And in defining GPDs like this and extracting them, Lorentz invariance is used in this parametrization. And so if you don't have a Lorentz invariant model, it's hard to extract these coefficients here. So that's why we use a I'll show you details, but I want to start with the summary before you get asleep. And what we found is the Polyakov sum rule worked. It worked both for the scalar spectator model as well as for the quark target model. But then this whole project developed a life on its own. What we found is that twist 3 GPDs exhibit discontinuities at x equal to plus and minus c. And even worse, if you take the forward limit, you go to PDFs. In most cases, these discontinuous contributions pile up to delta functions. And it turns out that these delta functions are essential if you want to test extended Burkardt-Cottingham sum rules, because if you don't include the vicinity of x is equal to 0, you may find such relations to be violated. Yeah.
So the delta function that you're mentioning here appears even if G2 is not little g2, but appears in exactly the same way as you have a delta at x equals 0 in little g2.
Yes.
Okay. Yeah, that's the delta. Yes.
So can I also ask a much less sophisticated question? So you have, do I understand it correctly, that for non-zero psi, you have some function of x and psi, which when you take psi goes to 0 limit becomes a delta function?
Yes. Yes. Get a representation for delta function. I'll show you some pictures. And before you get carried away, I mean, the first thing that crossed our mind when we saw these results is what happens with factorization of the twist 3 amplitude. And the short answer is they cancel. It's a miracle. I can't explain why it is. I can only show you the results that it does. There's probably a deep reason behind it, but I don't know it. Okay. So to convince you that there are delta functions, I need to show you a little bit about the details, how these calculations are done. So if you, to write down the most simple example, this is for scalar diquark. I mean, this is how you would calculate a TMD, and after integrating over K-perp, you get the PDFs. So we have, I should have drawn a diagram. So what we're looking at is something like this. Here I'm inserting an operator. And to get the PDFs, you integrate over the Lightcone K- first. And if you're only looking at the denominators, it's a great exercise in math methods, picking up the pole, etc., etc. And it doesn't matter whether you close in the upper half plane or lower half plane, except in one case you have a double pole, you have to be slightly more careful, etc., etc., etc. And when you do this integral, that's what you get done, okay? And if you have stuff in the numerator, in most cases, it's only infinitesimally more complicated, except if you get K minuses in the numerator. When that happens, all hell breaks loose, okay? Now at leading twist, and most of you have probably only done leading twist integrals like this. At leading twist, that can't happen because at leading twist, you have a gamma plus or a gamma plus gamma I. Important is you have a gamma plus, and any adjacent propagators that may contain a K minus, that part doesn't contribute. So you, at twist 2, you never get K minuses in the numerator, and if you get them, they're multiplied by K pluses. However, what does happen when you have a K minus here, and to illustrate what's happens, I've done a little algebra, and I've written K minus in a very complicated way, like this. There's a difference between these two terms. Just sit down and multiply them out after you look at the slide to convince yourself that this is indeed an algebraic identity. What this term does is it cancels that denominator. And suddenly you only have poles from these two here. And in the K minus plane, the poles are on the same side of the real axis. If you're not careful, you might reach the conclusion that this integral, therefore, is 0. If my poles are all on one side of the real axis, 0. The problem is that what happens when K plus is 0? Because when K plus is 0, nothing depends on K minus, and your integral is linearly divergent. Also, if you're doing a 2-dimensional or 4-dimensional integral of this expression here, just use the tables in Peskin and Schroeder, you get something non-zero, that's for sure. So what we have is a function that's, this question mark here is 0 when K plus is not equal to 0, because I can avoid the poles, and it's equal to something when you integrate over K plus. That's what Leonard calls a delta function.
Yeah, so this is the Lightcone,
Right.
yeah, and it's it happens with that twist 3 in these perp. Nobody talks about perp, but it's the Lightcone divergence, and you can't factorize it. It's the same mechanism that's happening. It happens at higher twists.
Right.
So you see it in the Lightcone. Great.
Yeah. Yes.
So maybe that's what Leonard said now, but in my language, I would say that, say, if you're using Lightcone perturbation theory, you're talking about the instantaneous terms.
I'm not sure it's that.
I'm not sure. I don't want to give them that name.
These are instantaneous terms, right? If you look at the quark propagator, the K minus in the numerator is the piece that gives you the instantaneous part of the quark propagator, and that's a piece which, as I understand, is causing the trouble. So really, and it makes physical sense. Look, if one of your quarks is instantaneous, of course it has 0 plus, right? It's not going forward in time. It's instantaneous.
No, I'm not fully agree. The instantaneous quark lines don't necessarily have zero momentum.
That's true. But
Yeah, because the Lightcone divergence has infinite momentum.
okay, let's take a step back. The K minus term in the numerator of the quark propagator is the one that gives instantaneous.
This part, yes. I mean, you can do something similar to this, but where you add and subtract the quark propagator itself. If you're doing that, then the part that cancels the denominator is the instantaneous piece.
Right. So
But it's not exactly what I did here. It's a different manipulation you're thinking of.
No, I know what you're saying. Just subtract the K slash, which is on shell, subtract and add it, right? The difference will give you the.
Right.
But
That's
you don't think that's what's causing this? So
You can actually, so I'll shut up in a second, but there's another way to do this to show that it's a Lightcone divergence is if you just take yourself a little off the Lightcone, regulate yourself, you get an e to the y or something, or e to the minus y, and then you go back into the Lightcone, you get a lot of k plus and this causes, right? One of them goes to zero. So it's really a Lightcone. In this case, it's a Lightcone divergence. I think.
I'll show how this looks like in the infinite momentum frame, hopefully. Okay. And if you're looking at PDFs, that's relevant for the following reason. I mean, here we have these relations between twist 3 objects and twist 2 objects, the extended Burkardt-Cottingham sum rules. So this is actually the Burkardt-Cottingham sum rule.
I mean, sorry. Yes.
For H chirally odd, you can derive something similar between H longitudinal and H1. And for the scalar E of X, there's the sigma term sum rule that relates the sigma term to the integral of E that Anselm talked about last week. So they have plans to measure E as well. And experimentally, you're never measuring X is equal to 0. I mean, even if you succeed to measure these twist 3 objects someday, experimentally what's going to happen is an integral from epsilon to not even 1, but hopefully close to 1. And then you're trying to make epsilon small. But you never push it to 0. So if you have a delta function or something that's very localized around X is equal to 0, you're going to miss it. And the conclusion will be that one of these is violated. And in fact, already a while ago with UG Koike, we did some studies in QCD, and the conclusion was that in QCD, actually, the first one, the Burkardt-Cottingham sum rule, to order alpha is fine, but the other two are in trouble. What you get is delta function terms already at one loop, and they are essential for these sum rules. Now for GPDs, it's a little more complicated. What you get is not a double pole where these have the same momentum, but because you have some momentum transfer, you get 3 different propagators, but you can still play the same game where you cancel out this propagator using the algebraic identity that I showed you before. And then you're left with these 2 propagators. And again, using the pole avoiding argument, the K- integral involving only these 2 propagators is non-zero only when K plus is between minus delta plus over 2 and plus delta plus over 2. So it kind of, only in that case is the real axis pinched between the 2 poles. And if you evaluate that integral, what you find is that in this region, it's proportional to 1 over delta plus, and outside it's 0. And for delta plus going to 0, that's a classic representation for a delta function that as I illustrated here. But so this kind of shows you how you can get the delta functions by going a little bit off forward, but it also brings up another potentially disturbing news, namely in factorized amplitude. If you use factorization, then in the DVCS amplitude, you get GPDs convoluted with 1 over x minus plus or minus c. And if you have discontinuities like this, you're done. And so these are examples of calculations that my student Fatma did of G2 and G2 tilde. I didn't define G2 tilde. G2 is defined with a transverse vector current. I showed you that one. G2 tilde is defined with a transverse axial vector current. Actually, G2 tilde in the forward limit becomes what's called little G2, the one that appears in G transverse. Sorry, I did not invent this notation. And what's shown here is in the quark target model as a function of x for different values of c, how these GPDs look like. And what you can see is they are discontinuous at x equal plus or minus c. And at least in the case of G2, that discontinuity grows when you make c smaller. And what you get is a representation of a delta function. Same for the scalar diquark model. In that case, both G2 and G2 tilde become big when c goes to 0.
Sorry, can I ask a
Yeah?
question? So this is my total ignorance of GPD calculations, but there's no cut. You don't need to cut through the vertex and the.
Yeah, it's an amplitude rather than a cut vertex.
So there's no imaginary part.
You can still pick up.
You see, continuing my previous question, right? So what you're canceling out is, you're right to remind me about how to get the instantaneous part. So your contribution comes from canceling out the denominator of the dashed line property. So then it's probably the instantaneous part of the dashed line that contributes.
We never talk. I try to avoid talking about the instantaneous lines. The way we do the calculation is just you calculate that like a vertex correction, except you don't integrate over k plus, because the k plus gives you the x dependence.
Right, but once you integrate k minus, you're sort of it should be equivalent to Lightcone perturbation.
It is equivalent to Lightcone perturbation theory, but since I like to avoid the discussion about instantaneous diagrams, I never use Lightcone perturbation
Can I
theory.
phrase my current question differently? I don't like instantaneous part, that's your right to do so, but I mean, if it's a cut line, you have a delta function, and then you have no issues, because the term which previously canceled the denominator of the propagator when it multiplies the delta function, just gives 0.
But these are amplitudes.
Right, so if you want to take the imaginary part, there would be no issue.
So
These diagrams have no imaginary part.
there's also I'm sure you know this, but there's a theta function which tells you whether you're in the physical regime or not. And so if you just start cutting these diagrams, without caring about the theta function that appears, you could get, for example, when you calculate the Collins function, you get non-universality, which I did some years ago by not paying attention to these theta functions. And so here the theta functions are, you just can't cut. You have to do the loop diagram and get pick up the poles that are consistent with the physical theta function that TS has pointed out.
So essentially, I missed the time over inside somewhere in the definition.
No,
When you say it's an amplitude, there should be a time.
You can phrase it in this language, but that's not how we approach it.
But if it's a correlator, and in summary you said, just to show the definition, here's a definition. If there's no time ordering, there should be a cut.
So this is the discussion that if you calculate these cut diagrams on the Lightcone, that they're equivalent time ordered products that Jaffe talked about, and the disconnected diagrams go away. This is a bit subtle, but there is a consistency between the two approaches.
Okay, maybe we can.
It's
Yeah.
So
Actually, I think so. Indeed, we have to move on because there's one more talk, and we have a discussion this afternoon. If there's something we can schedule a discussion tomorrow afternoon to go into some of these details.
So.
But yes, are you usually here tomorrow?
In the morning until lunch, late lunch. So these objects are discontinuous, and the first reaction was oops, because that's how they enter the DVCS amplitude, and you can wave your arms as much as you want, principal value, blah blah blah. You can't make any sense out of the integrals if the functions are discontinuous. However, this is how the twist 3 objects appear in the DVCS amplitude. It looks horrible, but the main point is they always appear in some linear combinations. It's never any of these functions alone that appears in the DVCS amplitude. And so it's only in these 4 combinations that all of these objects appear. And it turns out that in the combinations that actually appear in the DVCS amplitude, which for example are like this G2 plus 1 over XC G2 tilde, what we find is that these linear combinations are continuous at the points x equal plus or minus c, which is important for factorization, obviously. As a side remark, if you're doing the same calculation in a scalar spectator model, it's not continuous. It's only in quark target model that the relevant linear combinations are continuous. And since there has been so much talk about quasi PDFs, pseudo PDFs, I wanted to look at that stuff from that point of view, because I'm hoping to convince someone to calculate twist 3 quasi PDFs for the following reason. What's shown here is both the Lightcone calculation, so that's the same for all of them, as well as the quasi-PDFs. And the quasi-PDFs are just calculated very naively, no renormalization. We just use the cutoff and look at the momentum distribution of the quark inside a quark after it has dressed itself. And what you expect naively, and that's what you're getting for twist 2, is if your hadron, quote unquote, moves very fast, you get a distribution that scales with the overall momentum. You get a distribution that becomes a function of the momentum fraction only. And indeed, for the region x between 0 and 1, that's what you get. This part here, if you boosting to infinite momentum, it asymptotically approaches the light front calculation. But then you have a component right here that doesn't scale. And because it doesn't scale, it gets squeezed to the region around x is equal to 0, simply because you're expressing momenta in terms of fractions of the overall momentum. So in some sense, you get some component of the nucleon wave function that doesn't boost in the way you naively expect. And if you apply the machinery to translate this into a quasi PDF, what you should find is that for twist-free objects, that these delta functions pile up. And I should stop at this point here. So I've talked about twist-free GPDs, and one of the motivations that I gave you is transverse force tomography. The twist-free GPDs and PDFs, they exhibit properties that we're not used to from twist2. We get singularities such as delta function as x is equal to 0, which are important for various relations between twist2 and twist3. And for the GPDs, we get discontinuities, which fortunately in the linear combinations that enter the DVCS amplitude, the discontinuities cancel. I mean, we don't have a proof for that. This is what we observe at one loop. But one bad news that you may have guessed from this is if it's only these linear combinations where the discontinuities cancel that enter physical amplitudes, it's probably only these linear combinations that we will be able to measure even in the ideal world where we have perfect data and etc. etc.
You looked only at DVCS.
Yes.
There's also TCS.
Right.
Okay.
Yes. That statement I can only make for DVCS because that's all we looked at. Correct. Thank you.
Yeah, so one question, I mean, quite follow all the discussion, but how, you obtain these results, especially once the delta function in terms of the model, right? I mean, I don't even how to phrase the question, but how likely is it in the sense that what you find is just an artifact of the model? I mean, models are never perfect. They could, produce mathematical inconsistencies that are just not there in the real world. What makes you believe that this could be so serious that, for example, lattice studies should be useful?
Because if something goes wrong already in a one-loop calculation, it usually all goes wrong in general. That's the philosophy I have here. Of course, I have no proof, and that's why I keep pushing and pushing and pushing for people to do a lattice calculation that might show at least I mean, they will never see a delta function, but maybe they see the peak piling up. I mean, quark target model in some sense is, I mean, if you're looking at ultraviolet corrections, that's essentially taking the quark target model and looking at the cutoff dependence. So even if these delta functions and discontinuities are not there to begin with, I cannot see how you can avoid generating them once you look at scale dependence. I mean, of course, the evolution equations for all these twist-free objects are not closed. So this is, I mean, I can't use the scale dependence as a rigorous argument because I would have to know all the correlators that enter the evolution equations, which I don't. Yeah, that's why I would like to see a lattice calculation.
Right? Just thank our speaker again.
So yeah, so I feel